Hello, Kasakya Denis Nicholas, and I will be taking you through reinforced deep Q learning alongside Musasizi Jr. I'll be taking you through the introductory part, while my colleague will take you through the other parts. Uh, what you're going to cover, we have introduction to reinforcement learning, Q learning basics, limitations of Q learning, deep Q learning, uh, key innovations that's experience replay, target networks, applications and their examples, then challenges and advanced variants, as well as the conclusion. We'll start with reinforcement learning. Of course, reinforcement learning is a machine learning paradigm where an agent makes decisions by interacting with the environment to maximize cumulative rewards. So, taking you back to machine learning, the introductory part, machine learning has three paradigms. That's supervised learning, unsupervised learning, as well as reinforcement learning. Of course, the first two, supervised, it requires labeled data sets. Then unsupervised, it uses unlabeled data sets. So for this case of reinforcement learning, the agent interacts with the environment to make decisions. And of those decisions are there are rewards or penalties. Of course, rewards come after good performance, and then penalties for performing contrary to the desired way. So I'll take you through the key terms. We have the state, that's the current position of an agent in the environment. Then the agent itself, it is the entity that takes actions in each state of the environment. The action identified by letter A is the step taken by the agent in a particular state. Then the reward is the feedback signal that guides the agent. Uh, the episode, that's the end of the stage where agents can take new action. Of course, it happens when the agent has achieved the goal or failed. Then policy, that's the strategy the agent uses to select actions. Uh, I'll take you back using this example. I'll be telling you. Uh, so this is our agent. This is a 4 by 4 grid. This is our agent. Uh, this is where we aim to reach. And this whole 4 by 4 grid, it's the environment in which it is operating. So the episodes we have here, remember the episodes are like the endpoints. We have the lake, the holes having water. This is a frozen lake. The whole of it is a frozen lake. But there are sections where they are open water points. So we want the agent to move from this point until it reaches here. But it's going to move a number of states. So these squares represent the from 1 to all the way to 16. Those are all the states. Uh, so the actions is going to take, the steps is going to take, those are the actions, all the way from here to the final, to the goal state. So if I'm to bring you to the reward is this gift which is here. Then the actions, of course, actions are the steps it's going to take all the way from the first square to the 16th square. Then the policy. The strategies the agent is going to use to select actions, moving from the starting point back to the up the final point. So taking you back, this is the frozen lake is the environment where the agent is operating from, and but the step it takes or the action it takes is going to either be penalized or rewarded. And of course, we have what we call a queue a queue table. Of course, I'm going to take you through that in the next slides. So this is where you come into queue learning. Queue learning, it's a model-free, value-based of policy algorithm that will select the best series of actions based on the agent's current state. First of all, what's queue learning? Q stands for quality, and quality is what represents how valuable the action is in minimizing the future rewards. So each step it takes, it determines the reward in the future. Of course, these squares are given points. Maybe it can be each square can be given its own, let me say, numbers that you'll be used to give the reward for action it takes by the agent. I'll take you bit by bit. For model, it's a model free, meaning it doesn't require a model to take actions, while there are other model-based versions, on the contrary, which require models to take decisions. Then on the case of off policy, we have I can take an instance of you want to learn how to play chess. So off policy, you'll take tutorials from YouTube and you'll base on that to make decisions while playing your own game. But for the case of on policy, you play the game on your own and you keep on learning from try and error basis. So off policy, it the agent makes decisions based on some past instances, while on policy, the agent works on its own through trial and error. And from there, it gains experience based, it refers to the past instances to make decisions. So we have a Q value where the expected future reward of taking an action is stored. For the Q table stores the Q values for every state action pair. It stores the state as well as the action. So under here we have the Bellman's equation, where you have the learning rate and then the discount factor. So the Q function uses the Bellman equation and takes state actions as input. It takes states and actions as input. Then the equation simplifies the state values of state action value for calculation. So you can see the equation here. When you want to get the new Q value estimation, you'll have to use the former Q value estimation. Then you add the learning rate into the immediate reward plus the discounted estimate optimal Q value of the next state. Then you subtract the former Q value estimation. Of course, when you subtract the discounted estimate optimal Q value of next state minus the former Q value estimation, that's where you get the TD error. That's the TD error. So this is all the equation that you use to get those values that are stored in the Q table. So we come to deep Q learning. First of all, I started with Q learning, but Q learning had one problem. It would only act on few states. So instances that require many states, for example, a self-driving car, that one has a variety of states. So they couldn't be stored in a Q table. That's where deep Q learning comes in. So it involves using neural networks to represent the Q function of simple table of values. So the Q table always fail in high dimensional spaces. Yeah, that's what I'm just from giving an elaboration about. Uh, for the case, they can only manage to handle smaller states. But when it comes to large number of states, in an instance of self-driving cars, there it has states such as weather, traffic, the speed, the lane. Yeah, those are quite a number of states. So uh, a Q table wouldn't really be applicable in such an instance. That's why we come up with deep Q learning to help combat that anomaly. So the key innovations we have experience replay and target network. Under experience replay, the model will reference back to past instances. It recalls that the past instances that are stored within its buffer to be able to make decisions, as well as using target network. So for deep Q, much as it solves some the disadvantages of the shortcomings of Q learning, it also has its own limitations. Instability during training, because it requires data to be trained. So the shortcoming comes in when using inadequate data to train it. Then it is sensitive to hyperparameters. That instance, we have the learning rate and the discount factor. Those parameters, if those are the ones where the sensitivity comes in. Then high computational cost. Of course, it requires the high resources such as, of course, heavy computers as well as some other costs. Then you also have difficulty in handling large state spaces. There are those real life applications that really have many states, much as this deep Q learning came in to handle such an instance, but there are those which really have high number of states that it cannot handle as well. For instance, robotics, there it comes high, it has high number of states, so it comes as a limitation to it. Then generalization of to unseen situations. Of course, these models are not like humans, where you can use some persistence to refer to the other. The Q learning algorithm, deep Q learning algorithm will only act based on what it has experienced, not referring to the persistence, or it will refer to what it has only. It can't do the way humans can relate to some previous instance and correlate it with another one. Then you have data dependence. Of course, they require large data sets to be trained. Then you have space complexity. They really require a good number of states, making it complex. So my colleagues will be taking you through the next from deep Q networks. Thank you.
Okay, which will start with deep Q networks. So, last thing is visual enough. So I will start by explaining what deep Q networks are and how they can be applied. So, uh, it works. Learning. Um, the model just estimates the Q values and puts them in the Q table. But when we use deep Q learning, uh, now the models we use deep learning, we use the Q table. So it combines the two neural networks and Q learning, which we have talked about, and it uses both of them to train the network to approximate the Q values. Uh, then we have the techniques used in the deep Q networks. We have target networks and then the experience replay. Nicholas already explained the experience replay as the technique where the model uses the memory buffer to store experiences and update the Q function. So it will keep note of the experiences, all the Q values taken, and when when it experiences a state of six, it needs to speak as target networks, use networks to compute the Q, and then when we are computing the values to be put in the Q. Of course, then besides the target networks, we have the main network, which is a primary neural network based on the current state. Then DQ and or DQ learning in excuse me. We're here DQ networks in action. So DQ is a variation of CNN, neural network, and the outputs are classes by the Q values, or the key values or rewards will be corresponding to each of the actions the agent has learned and to take in response to the state environment. That is how we can use the deep Q into action. Then we have some challenges whenever we're using deep QN, rather DQN, which is deep model. We have challenges like overestimation, we have slow convergence, we have high dimensional inputs, and then sample inefficiency. So when you perform overestimation, this is where the DQN consistently predicts high Q values, and the solution to this challenge can be using the double DQN to decouple action selection and evaluation using two networks. Then slow convergence is where we have a very slow learning rate in our agent learning, and this can be solved by using experience loop as we saw it as a concept under target networks. Then also there is the challenge of high dimensional inputs. That is when we have very many states or quite a number of states input, rather quite a number of states faced by our model. So we can use CNN or configurational neural networks to handle this. Of course, this kind of high dimensional inputs can be like images, and CNN are good at processing these images. Then we have also sample inefficiency, where the DQN requires a large amount of data to learn effectively. So we have some solutions to these challenges. Of course, I've explained most of the solutions within the same slide as the challenges, that I summarized the challenge followed by the solution. Then we have applications of the DQN. So some of the applications can be like video games, where we use the DQN to train agents to play video games. A good example is the study game. It always becomes handy when we are at the superhuman level in playing that game. Then another application can be robotics. And within robotics, we can use DQN to train robots to navigate. We can use DQN to train them to avoid obstacles, and of course perform other tasks. Then another application of DQN can be autonomous driving, where automatic cars can use DQN in multi-state or in a high-dimensional state space. It can be used rather with autonomous cars. They shall be navigating in high-dimensional states where they shall need DQN networks to estimate the Q values. And another application is finance. Still, DQN can be used in financial applications. Then also healthcare is another application. Also, we have resource allocation as an application of this. Um, then in conclusion and future directions, as we have talked about reinforced learning and Q learning that comes under reinforced learning, and then deep Q networks that come under Q learning. So reinforced deep Q learning is a powerful technique within reinforcement learning, where neural network is used to approximate the Q value function, essentially estimating the expected value for taking a specific action in a given state. Now, this will allow an agent to learn optimal policies in complex environments in steady-state spaces, uh, while overcoming limitations of traditional learning, which struggles with high dimensionality, and more explanation from this part of application. Uh, I wanted to explain more on health, where we can apply BPM in healthcare. So BPM can be used to analyze patient data and suggest personalized treatment plans. This is how is this achieved? It's achieved by learning which treatment options are most likely to lead to positive outcomes and based on individual medical history. So another application was financial trading, and also have a simple explanation about it. DTN can be used to analyze market trends in financial trading, and decisions can be made based on the historical data, potentially identifying profitable opportunities by learning what for rather optimal buying and selling strategies. We have another application which I can add to this application system here, which is traffic management. So DKN can be used to optimize traffic light timing at intersections by learning patterns of traffic flow and adjusting light cycles dynamically to minimize congestion or traffic efficiency. So that's it. That's how I had for now. Thank you for watching our video and listening to our explanation. The topic that was assigned to us, which is reinforced deep learning. Thanks. Good night.